The tissues of the Permian. Now we're talking at a time in Earth's history where we're told amphibians lived on this supercontinent that was pretty much all one piece 260 million years ago. And the United States is sort of right in here, and that had to migrate 8,000 miles to get where it is today. So these bones were buried here and transported through plate tectonics 8,000 miles away, yet they show no abrasions or scarring of any kind. So I wonder, how did that happen? But this is where they are found today in Lawton, Oklahoma, and in the Texas red beds here in this country. They're also found in Russia and England and other places. So Carl mentioned this morning that the Cretaceous circumscribes the earth. Yes. So we feel that soft tissue is a cellophane wrapping around the entire earth as a reminder to us that the flood was global. And we intend to dig all over the world, if we're allowed to show this. Now remember too, the time frame. Not only was it an 8,000-mile trip, but it took place over 1,000-year periods. Would you like to live 1,000 years? I wouldn't. But imagine living 1,000 years. At the end of 1,000, would you say, let's do another 1,000? Let's go to 2,000 years. I don't know, you might be young and strong at that point, ready to continue. But multiply that 1,000-year period by 280,000. That's the number we're talking about in terms of age. It's incomprehensible when you think about it. We're talking about two organisms that we have studied so far. Eriops, he was about 6 feet long. Again, these are amphibious organisms that are found in these dig sites. The other one is Cacops. And you can see here some of the bones that Cacops produces, and we have some of those today. I won't let you hold these, but you can look at them. And so what we did is we decalcified these bones. We put them in a weak acid. And when we do that, the bone mineral just kind of deconstructs. So it kind of falls apart in the Petri dish, and then all the tissue falls out. And we can collect that, put it on slides, and study it. So that's what we've been doing. I'm not going to talk a lot about bone because it's on my previous videos, and you can. That's your homework class, all right? Go to the website, watch these previous videos, because I talk a lot about bone. But what I want to point out is what I mentioned to you earlier, is that these bone canals have the vessels and the veins traveling in them. Now, we weren't the first to publish on vessels. Other researchers have done that. But we thought, wow, well, if there's vessels in there, there must be veins. We were the first ones to publish on veins, and we did that in the September paper. No one had imaged veins before. We even found the valves that are in the veins. Remember, your arteries take the blood from the heart. It's under a lot of pressure. Boom, 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 right, with your heartbeat. Comes back how? Through the veins. Not as much pressure there. So there's valves to hold the blood while it moves up back to the heart. Those valves have been falling out of these tissues, and we've been staining them with RNA stain, and they're reacting positively to RNA. We're the first ones to publish that. But we reasoned that there would be veins in here, and we also reasoned that there would be nerves. See this yellow line right here? They show it here a little more clearly. Nerves, veins, and vessels travel in a triad. They're always together. And so we surmised, why not nerves? They should be there, right? If we're finding vessels, we're finding vein valves, shouldn't we find nerves? And that's what we've been finding. That's why we went to look for them, and we're finding them.